The universe can be imagined as a massive interconnected symphony where every particle and force vibrates together in a cosmic rhythm. But on the date known as the 15th of January 2026, that harmony was suddenly interrupted in a way no one expected. Picture the most advanced observational systems humanity has ever built, multi-billion-dollar instruments orbiting silently in space, designed to watch the universe with incredible precision. Now imagine all of them blinking out at the exact same moment, almost as if something in the darkness decided it did not want to be observed. At precisely 18:04 UTC, the Transiting Exoplanet Survey Satellite, better known as TESS, prepared to focus its powerful sensors on an unusual interstellar visitor called 3I Atlas. Scientists had been waiting for this exact moment because the object was about to cross through sector 1751, the ideal observation window where the satellite could capture the most valuable data. This alignment offered a rare opportunity for humanity to analyze the detailed telemetry of something that originated beyond our solar system. But at the exact moment this observation was about to begin, the unexpected occurred. The spacecraft did not simply glitch. It did not briefly lose signal or experience a small technical error. Instead, TESS abruptly entered deep safe mode, a protective shutdown that immediately cut off the scientific data stream. For the next 67 hours, the satellite remained silent. Those hours were critical. During that time window, 3I Atlas continued its movement through the sector where scientists expected to gather the clearest and most detailed measurements of its structure, motion, and composition. The opportunity to observe the object at its most revealing point was suddenly lost, leaving researchers with a massive gap in the record. But the strange silence did not start with a satellite. Just a few hours earlier, at 14:30 UTC, another surprising event had already taken place much closer to Earth. The International Space Station, one of humanity's greatest technological achievements and the symbol of our ambitions in orbit, was suddenly placed into a state of emergency. A mission known as Crew 11 was terminated months earlier than planned due to what officials described as an urgent medical issue. The response was immediate. The astronauts were ordered to leave the station and return to Earth through an emergency deorbit procedure. For space missions, such a decision is extremely rare because evacuations are only used when there is a serious risk to the lives of the crew. The station's operations were abruptly halted, and the crew capsule began its descent back to the planet. Yet when the capsule finally splashed down and the astronauts were examined by medical teams, something unusual became clear. Every member of the crew was reported to be healthy. No life-threatening illness was detected, and no clear explanation was given for why the evacuation had been necessary. When viewed together, these two events raise a difficult question. What are the chances that the two most important observation points in Earth's orbit, TESS, and the International Space Station, would both experience critical interruptions on the same day during the same 6-7 hour window, while tracking the same mysterious 3 billion-ton interstellar object? When we examine these events through the lens of modern physics, the coincidence becomes even harder to ignore. In the verified science of statistical mechanics, probabilities help us understand how likely independent events are to occur at the same time. When researchers analyze the timing of the TESS shutdown and the sudden evacuation of the International Space Station, the numbers produced a startling result. The chance of both events happening within the same narrow 6-7 hour window purely by coincidence is estimated at roughly 1 in 877,000. In scientific terms, that is not simply unusual. It is a signal that something else may be influencing the system. To understand why the TESS failure matters so much, we need to look at how satellites like it normally operate. In the verified science of orbital photometry, telescopes such as TESS detect extremely small changes in light. By watching distant stars and measuring tiny dips in brightness, scientists can discover planets orbiting other suns. That same method can also be used to analyze unusual objects moving through our own solar system. By studying the light curve of an object, astronomers can determine its rotation, speed, its shape, and even clues about the material covering its surface. TESS was perfectly positioned to collect this type of data from 3I Atlas. The satellite sensors were aligned for what scientists considered the forensic gold standard of observation, but simulations of the spacecraft systems reveal something strange. According to engineering models, a simple technical error would normally leave a clear trail in the telemetry voltage spikes, temperature shifts, or corrupted data packets. None of those appeared. Instead, the shutdown resembled what engineers call a clean transition, the kind that might occur if an external electromagnetic signal triggered the satellite's automatic protection systems. Some theoretical models even suggest a more unusual possibility. A localized electromagnetic pulse, or an interference pattern affecting higher dimensional space, could theoretically force a spacecraft computer to enter safe mode without damaging any hardware. In that scenario, the satellite isn't broken. It is temporarily blinded. If we apply what physicist Michio Kaku often describes as the Kaku scale of advanced civilizations, the implications become even more thought-provoking. A civilization, classified as Type 2 or Type 3, would possess energy resources far beyond anything humanity currently controls. For such a civilization, the silicon-based electronics used in our satellites might appear extremely primitive. In theory, a narrow beam of directed radiation from deep space could quietly disable those systems without leaving a destructive trace. To understand the second half of this mystery, we must look closer at the environment surrounding the International Space Station. The ISS orbits Earth at an altitude of about 420 kilometers, protected from the harshest solar radiation by the planet's magnetosphere. In the verified science of space medicine, evacuating astronauts is considered the absolute last resort. Such decisions are only made when there is a direct threat to human life or a catastrophic failure of the station's life support systems. Yet in the case of the Crew 1-1 mission, details surrounding the emergency evacuation remain extremely limited. Through the lens of theoretical physics, some researchers have proposed an unusual idea. If 3I Atlas were producing a low-frequency resonance, a subtle vibration in the structure of space-time itself, it might interact with sensitive electronics or even with human neural systems. In that scenario, the International Space Station could have unintentionally become a kind of resonance chamber, amplifying a signal that humanity is not yet technologically advanced enough to interpret. And this possibility leads directly to the next mystery, the significance of the 6-7 hour gap in our observations. In the science of information theory, the absence of data can sometimes be more revealing than the data itself. When scientists lose a portion of a record, especially during a critical observation window, the missing information can hide events that completely change our understanding of what happened. In the case of 3I Atlas, the 6-7 hour blackout created exactly that kind of blind spot. During those nearly 3 days, humanity lost the opportunity to confirm several unusual characteristics already associated with the object. Astronomers had previously documented 27 different anomalies in its behavior. These ranged from the unusual pattern of its surface, which appeared to show a hexagonal tessellation, to small but measurable accelerations that could not be explained by gravity alone. In the verified science of astrodynamics, the path of any object moving through space is normally predictable. Once its mass and velocity are known, the equations of general relativity determine how it will travel through the gravitational field of the Sun and the planets. But the strange thing about 3I Atlas is that its trajectory has not always followed those predictions perfectly. If the object performed any kind of propulsion maneuver during that 6-7 hour gap, we would have no direct visual record of it. All astronomers could see would be the object's position before the blackout and its position afterward. The moment of transition, the point where something might have changed, would be completely hidden. Some theoretical models suggest that the blackout might have acted as a temporal delimiter, a short window of darkness in which the object could adjust its course without being observed by Earth's monitoring systems. Whether this involved conventional propulsion or something more exotic remains uncertain, but the possibility raises questions about how advanced technologies might interact with the laws of physics. If we again consider the Kaku scale, a civilization far more advanced than ours might not treat physics as a set of strict limitations. Instead, those laws could become tools. One idea involves gravitational lensing, a phenomenon predicted by Einstein's theory of relativity. Normally, extremely massive objects like galaxies bend the path of light around them, creating distortions that astronomers can observe from Earth. But imagine if an object could control that effect on a much smaller scale. If 3I Atlas possessed a form of gravitational dipole, it could theoretically bend light around itself in such a way that photons from TESS's cameras never actually reached its surface. To the satellite's computers, the incoming data would appear contradictory or impossible to process. Faced with that type of conflict, automated safety systems might shut down to prevent a catastrophic logic failure. From this perspective, the satellite's sudden safe mode event might not represent a malfunction at all. It could be the result of encountering a phenomenon that its programming simply wasn't designed to interpret. When we examine the timeline again, the pattern becomes difficult to ignore. On January 15, during the exact moment humanity attempted to observe 3I Atlas at its closest and most revealing angle, both our orbital telescope and our largest inhabited space station became effectively blind. One shut down, the other evacuated its crew. And as the investigation into the missing data continues, scientists are beginning to ask a deeper question. If something truly happened during those 67 hours, then the most important mystery may not be why we lost the data. The real mystery might be what occurred while no one was able to watch. To understand why the sudden 6-7 hour blackout triggered quiet concern among scientists, we need to look at one of the most fundamental principles of physics, the second law of thermodynamics. In simple terms, this law explains how systems naturally move from order toward disorder. When machines fail, they usually fail in messy and visible ways. A satellite malfunction typically leaves behind warning signs, temperature spikes, unstable voltages, corrupted telemetry signals, or gradual performance decline. Engineers expect to see a trail of chaos, but the shutdown of TESS on January 15 did not behave like a normal technical failure. Instead of a gradual breakdown, the system shifted instantly from full operation to total silence. There was no warning pattern, no damaged hardware signature, and no chaotic telemetry sequence. In the verified science of reliability engineering, a failure that clean, especially during a critical observation window, raises the possibility of an external trigger rather than an internal breakdown. This is where some researchers begin to examine the scenario through what is often described as the Kaku perspective on advanced civilizations. If an intelligent technological system far more advanced than ours existed somewhere in the cosmos, it could theoretically interact with our electronics in ways we barely understand. According to theoretical models, a sufficiently advanced technology could use directed energy transmissions, such as narrow microwave beams or extremely focused laser pulses, to temporarily reset silicon-based circuits. In practical terms, that means a satellite could be forced into safe mode without being physically damaged. Data simulations suggest that during the moment of orbital alignment, the International Space Station and 3I Atlas were briefly positioned along the same line of sight. In the verified science of electromagnetics, if a sensor is overwhelmed by a coherent electromagnetic frequency, its logic systems will automatically trigger protective shutdown procedures to prevent permanent hardware damage. From that viewpoint, the event looks less like a malfunction and more like a deliberate interruption, a cosmic version of someone quietly saying, "Be quiet." The statistical evidence makes the situation even more intriguing. The ISS has supported more than 270 missions throughout its operational history, and early mission terminations caused by medical emergencies are extremely rare. Meanwhile, TESS operates with a reliability rate of about 99% uptime. For both systems to experience major operational interruptions within the same narrow observation window is statistically extraordinary. If we interpret this through the lens of quantum probability, the two events may not be independent at all. Instead, they could represent what physicists call a correlated state, where separate systems are influenced by the same external factor. Some theoretical explanations suggest that 3I Atlas might have used the 6-7 hour period to activate secondary systems while our monitoring instruments were temporarily disabled. If that were true, the blackout would not represent a failure in our observational network. Instead, it would represent a successful moment of concealment, and the most unsettling detail may not be the shutdown itself, but what happened immediately afterward. When the 67 hours finally passed and TESS returned to operation, astronomers began comparing the new observations with the object's previous trajectory. What they found introduced an entirely new layer of uncertainty. According to the verified science of orbital mechanics, any object moving through the solar system follows a path determined by gravity and momentum. Once those parameters are known, its movement can be predicted with remarkable precision. Yet, after the blackout period ended, 3I Atlas was no longer exactly where scientists expected it to be. The change was subtle but measurable. The object had shifted from its earlier hyperbolic trajectory and appeared to settle into a slightly different path through the solar system. In the science of ballistics and orbital motion, altering momentum normally requires energy. Rockets, for example, produce visible exhaust plumes and intense heat signatures when they change direction. Those energy releases create detectable thermodynamic footprints. But in this case, no such evidence appeared. Infrared instruments searching for thermal emissions detected no plume, no heat spike, and no burst of energy consistent with propulsion. In other words, the object seemed to change course without producing the thermodynamic signals physics normally demands. This is where some theoretical physicists begin considering far more exotic possibilities. Through the lens of string theory, matter is described as patterns of vibration in tiny fundamental strings. If a sufficiently advanced technology could manipulate those vibrations, it might theoretically alter how an object interacts with space itself. Instead of moving through space in the conventional sense, the object could shift the surrounding space-time structure. In that scenario, the craft does not accelerate like a rocket. Instead, the geometry of space moves around it. Although this idea remains speculative, it would explain why no conventional propulsion evidence was detected. The object would not be pushing against space, it would be rearranging space. Another curious feature of 3I Atlas is its 7-1-hour rotational cycle. Data analysis indicates that this rotation has remained remarkably stable. In natural asteroids, rotations often fluctuate due to gravitational interactions or collisions, but a stable, controlled rotation can also serve a mechanical purpose. Some theoretical models suggest that maintaining such a rotation could generate a form of gyroscopic stabilization, protecting internal components from extreme acceleration forces. If the object performed a rapid relocation during the blackout period, such stabilization could help maintain structural integrity. From that perspective, 3I Atlas may not behave like a drifting rock at all. Instead, it resembles a precisely balanced system, like a spinning top that refuses to fall. And if that interpretation is even partially correct, the implications extend far beyond a single astronomical observation, because it would mean the 6-7-hour silence was not simply a lost data window. It might have been the moment when humanity briefly lost control of its own observational awareness. The final stage of this investigation leads to one of the most unsettling possibilities of all. When the blackout ended and TESS resumed communication, scientists expected the surrounding environment of space to return to its usual chaotic background noise. Instead, instruments connected to the Deep Space Network detected something unusual near the coordinates where 3I Atlas had performed its mysterious maneuver. The sensors recorded a coherent resonance. In the verified science of signal processing, coherent signals maintain a constant phase and frequency over time. Natural cosmic sources rarely produce signals with that level of stability. Most astrophysical radiation is random and noisy. A coherent resonance, by contrast, resembles a carefully structured transmission. Through the lens of theoretical analysis, this raises a fascinating possibility. The 6-7-hour blackout may not have been an accident or a malfunction. Instead, it could have been part of a much larger interaction between our technological systems and whatever phenomenon 3I Atlas represents. Some scientists have speculated that such an event might resemble a sentinel handshake, a brief exchange of signals designed to test whether a planetary civilization possesses certain technological capabilities. If that interpretation were true, then the blackout may have served as a way to temporarily disable local sensors while the object performed operations that were not meant to be observed. The gravitational behavior of the object adds another layer to this mystery. According to general relativity, the gravitational field of an object should remain closely tied to its physical location. However, data simulations conducted after the January 15 observations suggest that the gravitational influence of 3I Atlas may not perfectly match its visible position. One theoretical explanation involves frame dragging, a phenomenon normally associated with extremely massive rotating objects such as black holes. In frame dragging, the rotation of mass can twist the surrounding fabric of spacetime. If a smaller object somehow generated a localized version of this effect, it could distort the way observers detect its true location. While such an idea remains highly speculative, it illustrates how unusual the data surrounding this object appears to be. As researchers continue to analyze the telemetry, another observation has become clear. During the blackout window, Earth's magnetosphere briefly showed unusual patterns known as magnetic flux ropes, structures normally associated with solar storms. Yet during that period, the Sun itself was relatively quiet. If the object interacted with Earth's magnetic environment in any way, it would suggest a level of influence far beyond what scientists normally expect from an interstellar visitor. All of this leads to a profound shift in perspective. For centuries, humanity has looked into the sky, believing we were the ones doing the observing. But the events surrounding January 15 suggest a different possibility, that our instruments were not merely studying something in space. They may have been noticed. Whether 3I Atlas ultimately proves to be an unusual natural object or something far more complex remains an open question. But the mystery of those missing 67 hours continues to challenge our assumptions about what we can truly detect in the universe. And if you want to stay updated as scientists uncover more clues about this cosmic mystery, make sure to like the video, subscribe to the channel, and share your thoughts in the comments below.